we'll just use that. I think our life is Awesome. Could folks start sitting down now? We're going to start the lightning talks in about 1 minute. So, let's see. Who have we got? Could people who are giving lightning talks today come and sit in the front row? I guess that'll be easier. And I can just pull up a list of who we've got doing that. Actually. Great. So we've got lightning talks, going to be 6 minutes each. Please try and keep to time. We've got James here in the front row, who's going to be doing timing. He'll be showing a green light up till 5 minutes, 30 seconds, then a yellow light until 6 minutes, and then a red light afterwards. And if you finish before 6 minutes, then we'll take some audience questions. But if you go too long, then we'll just move straight to the next lightning talk. Great. I think, and we've got 10 lightning talks for this session, and we've got the remainder of the lightning talks tomorrow. I will just hand over now to Jason, who's starting us off.
Hi, everyone. I'm Jason. I'm going to talk briefly about emergent abilities in language models. I work at OpenAI, but apparently when I was reusing these slides, I had forgotten that. So I guess in the past couple of years, we've been used to seeing these predictable gains as a result of scaling. So here are the sort of canonical scaling law plots where, as you increase the compute or the data set size or the number of parameters, you get this sort of predictable improvement in the test loss. But I think what I'm going to be talking about is sort of this unpredictable phenomena that we call emergence. Basically, emergence is sort of this concept in science that it's like a qualitative change that arises from quantitative changes. And I think it sort of started with this more is different paper by a Nobel Prize winning physicist. And then I sort of like these examples from one of Jacob's blog posts. So like, for example, with a bit of uranium, nothing special happens. With a large amount of uranium packed densely enough, you get a nuclear reaction. Or with DNA, like given only small molecules such as calcium, you can't meaningfully encode useful information. Given larger molecules such as DNA, you can encode a genome. In terms of large language models, this is sort of the definition that we used. It's not perfect, but I think it encapsulates a lot of what we're interested in. So the definition is basically an ability is emergent if it is not present in smaller models, but is present in larger models. And in this particular paper, we focused on training flops as the measure of like how large the model is. You can do it with number of parameters or trained data set size as well. Before Chinchilla, usually you train on like the same data set size for each model size. So then, training flops would kind of be similar to model parameters. And the first sort of scenario where we've seen like a lot of emergent abilities is in few-shot prompting. And if you don't know how few-shot prompting works, you can ask, but basically we define like a few-shot prompted task as emergent if it achieved random accuracy for small models, and then it did like much better than random for large models. And the way that we were sort of thinking about this is that we sort of had these plots. So each sort of plot is a different NLP task. And then the x-axis is like the scale of the language model. So like as you move right, the scale increases. And then the accuracy is on the y-axis or whatever metric you use for the task. And then we plotted like basically a bunch of different language models from OpenAI, Google DeepMind. And I guess the point here is that like for the small models, the performance is sort of flat or about random. And then once you pass like a certain, model scale threshold, the performance suddenly jumps to well above random. And here's an example from MMLU of like one of these tasks that are emergent. Yeah, so here's another quick example. So there's this like inverse scaling benchmark that I really like. And basically they were looking for tasks where the model performance decreases as you increase the scale. And there's sort of some tasks where if the small model would do well, so this task is kind of tricky and you're supposed to say glib. And then the medium-sized model sort of gets fooled into saying gold because it knows like the phrase all that glisters is not gold. But then the large model can actually recover and get this like emergent improvement in performance and get 100% at least on this task. Another quick example of an emergent ability is chain of thought prompting, where you add like the reasoning before you give the answer. And here's sort of an example over like a bunch of models and different data sets. So the y-axis here is like the average on like 16 data sets. And basically for small models, the small model can't really output like a coherent reasoning chain, so it does worse than if you actually don't ask it to give reasoning. And then large models see this huge boost on these like tasks that require reasoning. And then another cool example is like there's some tasks where like if you don't use chain of thought, you'd get basically flat performance, and it would seem kind of hopeless. But you can sort of unlock this emergence if you use chain of thought. So yeah, as a quick summary, basically emergent abilities are sort of only observed in large models. There's a bunch of caveats here that we can definitely discuss later. And their emergence sort of can't be predicted by scaling plots if you only look at the small models. And then I guess I'm running out of time, but yeah, we basically saw it as like a framing for how to view like scaling. Yeah, thanks. Okay. Yeah. Yeah, that's a good question. I think, yeah, definitely maybe training loss is another good way. Like that could be a good x-axis. But I don't know if like that many empirical data points where like a small model has like the same training loss. I guess it's hard to like control for like what data is held out. Yeah. Thanks.
Awesome. Next up, we have Martin, and then next Bean.
Great, thank you. So I want to talk about world models that emerge in these systems, and I'll just be concrete about what I mean with an example. This is from recent research where we were looking at what do sequence models learn when they learn a sequence. And we took a toy situation. We said, we'll take the game of Othello. And what we're going to do, this game, it's got slightly non-trivial rules, but it's not like Go. What we'll do is we'll train a language model just on sequences of moves from real life transcripts of the game. There's no a priori knowledge of the game. It's just seeing tokens. And you can ask, does it learn to play the game? The answer is yes. This is not hugely surprising given some of the emergent abilities we've seen already. But the second question is, how is it doing this? And this is kind of interesting because just figuring out the legality of a move depends, you need to know the board position, but all it has is these moves. And so you could guess maybe it is somehow reconstructing the board position. And it turns out you can do a bunch of experiments and discover that yes, it does have a representation of the board. It plays a causal role in the predictions. Another researcher, Neil Nanda, has actually recently sort of extended and simplified this, so I feel sort of confident in saying it. It's built a model of its little world, the world of Othello. Okay, so this leads me to my current hypothesis, which I'd say is still speculative, that high-performance systems are developing models of the world, and they are knowable. And there are a lot of people, I think, in this audience who have done more work here than I have, and I sort of lean on their evidence as well. Okay, so what do we do? Why do we care? Let's think, I'm going to get speculative here, and this is thoughts with my colleague Fernanda Viegas. Let me show you something that Fernanda noticed. She talks to ChatGPT in Portuguese, and there's an interesting thing about Portuguese as a language that you have to decide the gender of the person you're addressing. And I've highlighted points in here where ChatGPT has done this. The beginning of this transcript, it starts out with sort of a default masculine. Fernanda mentions wearing a dress. Next time an address it needs to choose, it chooses feminine. And this is a funny thing she sort of noticed as she talked to it. Not surprising, again, right? It's a language model. Its training data says it should do this. But what does the world model hypothesis say? It says it's not just a random collection of statistics, but something interesting happened. A model of the user has changed. Now you could ask, in this case of Portuguese, we could just see this, but in English, maybe we can't. It's still happening. Let's ask ChatGPT. Well, I tried asking it what gender it thought I was, and it gave me what I would say is a blatantly dishonest answer. It actually volunteers that it does not make any assumptions based on, say, my name, which if it's a language model, it doubtless is doing. And I would just point this out as an interesting example of the tension between user experience design and honesty and deception. It's not clear to me that this is the wrong choice to say, but it is, you have a neural network being deceptive about what it is doing. Okay, so given this, let's think about how else we might get information. And I want to talk about instrumentation. There's sort of this study in contrast if you look at the machines around us, which is that all the everyday things we use are constantly telling us about their internal state. The oven says it's hot, my Subaru says there's all sorts of problems. And this Tesla over here, this is Fernanda's Tesla, is actually showing you a world model of what it thinks is happening. Now, this was put there by engineers. You might say, oh, that's very different from the case of a chatbot. But if we believe the world model hypothesis, maybe it's not so different. Maybe we should be showing these things. And so that leads to the question of what world model should we show? Obviously task dependent, but I would claim there are two world models we should all be looking for, trying to extract and displaying. The U model, the model of the user, and an I model, the model of the system. I think in almost every situation, you want to know these things. And, we've seen with transcripts from Bing that something is happening here. And, it might be very useful to know, like, is it trying to make stuff up or not? Okay, so I want to end with sort of an interface provocation here. And I'm not saying this is a recommendation. This is a provocation. It's a mock that Fernanda made, showing, imagine if you had a chatbot and you had a little readout next to it saying various things that it thought about you or that it thought about yourself. Maybe it's judging you. Maybe it's judging itself, whether it's being a good Bing or not. Would this be useful? Or would it be horribly offensive? I think there's a really interesting space for both machine learning research to extract this information and also for interface design to figure out what we want to display, what is going to be helpful, and perhaps it will maybe even give us a sort of information asymmetry over these machines. We may be able to get things from instrumentation that it can't know itself, and that could be helpful for safety reasons itself. So just end there, that my current speculation, world models exist, we can find them, and they're immensely useful for AI interfaces. Thank you.
Any questions from the audience?
In one of your slides, you mentioned that you expected world models to be interpretable, understandable, non-interpretable. Can you say a little bit more about it?
Yeah. Yeah, I don't want to say anything too strong here. In fact, my guess is that there are a bunch of understandable models, and then there may be stuff that we don't know that is just stuff it's memorized or can't do very well. However, I also sort of believe in a principle of least drama in life, and we should at least consider that instead of like vast chaos of surface statistics or incredibly alien thoughts, if we're talking about something that's a basic part of the world, there may actually be a simple representation there.
Thanks so much. Now we have Bin and next Jascha.
Thank you. I'm Bean. I'm going to talk about alignment, setbacks, and beyond alignment. I work at Google Brain. According to the definition that I stole from Wikipedia, alignment means that humans' objectives perfectly align with machines' objectives. Great, everyone is happy. But of course, it's going to be, oh no, the slide is broken. Of course, it's going to be a journey. First, we kind of have to figure out what are our objectives. It's not an easy question. Lots of people in this room trying to answer this question and beyond. What does fairness means to us? At the same time, on the technology side, we've been trying to develop a tool that could reveal machines' intention or objectives. And most of the time, these tools and a lot of my past work falls into this category, interpretability. A lot of times we think about machines to reveal their intention first, and then humans look at it and make their own judgments. This area of interpretability had gained a lot of interest. Lots of people developed a lot of tools. Unfortunately, a lot of recent work showed that a lot of these tools don't work as expected. And I happen to participate a lot along this discussion in revealing setbacks. So I'm going to talk about that briefly. So in the past few years, I've been focusing on slightly different kind of alignment. Creating new things, making discoveries in science and medicine is one of the core objectives of humans. So what if instead, what if we can aim to teach humans something new? So why is this an interesting and useful goal? Well, I still think that aligning existing human values to machines' objectives is an important goal. But many setbacks made me realize that no matter how much we try, there will be a gap between how we express our objectives in our language versus how machines do. Just because we use very different bases, we have different experiences, we have different goals. So counterintuitively, trying to teach humans and have them fishing out this ultimate form of what's useful for them can build the basis for revealing the truth in machines. So I'm going to talk about that briefly. Setbacks. You're probably familiar with saliency maps. You have an image network. Each pixel is marked with a number, how important each pixel is for prediction. A definition of importance is that it reveals something about the shape of the function around that pixel. So is the function going up or down or flat? Now, one of our recent work shows that our expectation of how this tool works is completely misaligned. So in other words, what is our expectation? Our expectation is that if the tool assigns 0 attribution, then it means that it's not used by model F or it is insensitive to perturbations of this feature. And that's how it was advertised in the original paper. It was how it was used in Nature for medical application. Turns out that's all wrong. We can theoretically prove that none of these seemingly naive inferences are true. So not only that these tools cannot reveal machines' objectives, it should definitely not be used for high-stake decisions. And these are just one of many setbacks that we encounter. Next, I'm going to talk briefly about the teaching humans new things. I was excited that Ilya talked about AlphaZero today. We have this paper that came out last year where we study how AlphaZero, this is self-trained superhuman chess playing machine from DeepMind, how it acquires chess knowledge. And in that, we show what kind of human chess concept appear where in the training process, where in the layer in the AlphaZero, and when within its training process. Now, another thing we did there is to compare how humans' opening moves evolved compared to AlphaZero. And if you look at just the colors, and opening moves are like first couple moves you play in the chess, they're very different. And that begs the question, how is it different? What are they doing differently? So in an ongoing work that's I'm very excited about, we are teaching chess champions a new superhuman chess playing concepts. A method is pretty simple. I love how simple method can be often powerful. We're discovering new chess strategy by removing known existing chess concepts and leveraging the relationship between new and existing concepts. And what I love about this work is evaluation. The Magnus Carlsen, the world's chess champion, just said yes to us, that he can solve some chess puzzles for us. And we're going to see if we can teach him some new chess strategies. And of course, this work is only possible because the first author of this work is champion herself. Her name is Lisa, and a machine learning PhD student at Oxford who is working with me on this. So lots of interesting, exciting directions. This will probably come out in a few months. We're almost there. Oh, I'm missing last slide. But yeah, excited to chat a lot more about other useful directions in alignment. Jacob. We're doing a bunch of different things. It's pretty complex. We're basically thinking about looking at the value, policy value network, and look at MCTS and solving convex optimization problem within it to learn a vector that represents not something existing, that we regress out the existing concepts, but we're doing 10 other things to make sure that everything is removable, they're removed. Lots of evaluation. Thanks.
Just the fact that Jascha, we have Tegan.
Cool. Hey there, I'm Jascha. I'm also at Google Brain. So I am going to tell you about a little bit of an exploratory experiment that suggests that as agents become more intelligent, they become less objective seeking, which would have some obvious like impacts on which risks we think are the most important risks. So to start, this is maybe the common narrative of like existential risk from AI, which is we're going to build machines that are smart as us, and then quite rapidly they will either make themselves or we will make them much, much, much smarter than us. They're going to be super intelligent, and these super intelligent machines are going to be super duper effective at achieving whatever goal they are set on. And if that goal is slightly wrong, then we are in really bad shape. This is many steps of speculation. So are there any of these steps that we could somehow like experimentally ground? And I'm going to pull out one of these here, which is this idea that super intelligent systems will also be super goal seeking or super effective at pursuing their goals. And just to say something about what this means, let's imagine like a 2D plane where the x-axis is how intelligent you are and the y-axis is how coherent you are or how goal seeking you are. So in the upper left, you have stupid machines that are really effective. They like thermostat adjust your temperature perfectly. In the lower left, you have stupid machines that are also effectively broken or unpredictable. In the upper right, you have like monomaniacal like AGI or like paperclip maximizers. And in the lower right, you have a hot mess. You have an AGI, which is super duper intelligent, but can't be relied upon to do any kind of goal in a trustworthy way. And so the kind of standard existential risk says we're going to end up somehow in this upper right corner. I personally suspect we may end up taking a trajectory that looks kind of more like this. And the machines are going to get smarter, and the AIs are going to get a little bit less coherent, and they're going to misbehave in possibly unpredictable ways. But I said we were going to test this, so let's see if we can test it. So I did a test. I asked 3 groups of naive subjects. These are just like colleagues and friends. They're all either PhDs or pursuing a PhD in like relevant fields. I asked first for one group of them to propose just a list without knowing what the experiment was of ML models and living creatures and human organizations. And then in step 2, I asked another group to sort that list by intelligence. And in step 3, I asked the third group to sort that list by coherence. And so what are the outcomes? So let's start by looking at how they judged AI models. So human subjects who are roughly experts in this field judge that as AI models move from like less intelligent, like a linear classifier, to like more intelligent, like GPT-3, that they also move from more coherent to less coherent. They become less goal-seeking as they become smarter. But I didn't just look at AI models. We also looked at animals, both non-human and human. And we also looked at human organizations. And for all 3 of these, you can see this trend from the upper left to the lower right. So at least based upon subjective human judgments, as you get smarter, you also become less coherent in your behavior and you become more of a hot mess. So to summarize, AI can maybe be misaligned for 2 different reasons. It can either be misaligned because it's monomaniacally pursuing some like undesirable goal. It's like a paperclip maximizer. or it can be misaligned because it acts in ways that don't pursue any kind of consistent goal. So it can be like a hot mess. As we make AI smarter, I think the second of these is more likely than the first. I did a small subjective study, which you can poke lots of holes in, but I think it's interesting. And the outcome of that was that people judge the entities become less coherent, AKA more of a hot mess, as they become more intelligent. I will say both a super intelligent hot mess and a super intelligent paperclip maximizer, they each have their own set of risks. This does not mean that it's safe, but it does maybe change the profile that we should be thinking about. Jason, David.
Do you have ideas for why this would be the case?
Yeah, so I actually think that, sorry, I'm taking a little bit longer to try to phrase this concisely. So when we ask a complicated dynamical system to maximize an objective function, we're trying to put a very strong constraint on that dynamical system. And the more complex a dynamical system is, the harder it is to impose the strong constraint. In fact, the strength of the constraint, like the more degrees of freedom it has, the stronger the constraint even has to be. And so I believe that as you make this dynamical system, which is the AI, more and more and more complex, it becomes harder and harder and harder to yoke it to any purpose at all. In that it's more likely just to behave like a dynamical system with like attractors and spurious dynamics and like all kinds of weird behavior. Yeah.
Love it. I agree with the complication and I guess my concern is this kind of lack of coherence is sort of out of general generality, general intelligence, or maybe like organic model. So the less intelligent things are narrow, whereas more intelligent things tend to be sets of has multiple functionalities. So maybe what you're seeing is just multiple functionality, looks like less coherence, or this general intelligence. I think this is what the story you just talked about. It's not as it's more mixed.
Yeah, I think interpreting this is we should have a longer conversation later. I completely agree. Like it could be that things are getting less coherent, but are still getting more coherent, still getting more capable at goal seeking because they're getting more powerful, like faster than they're getting less coherent. It could also be that we're just less able as humans to judge the actual goal of systems as the system gets more complex. Like there's a whole bunch of explanations. I totally agree.
Very quickly, I was just going to say, I mean, if becoming really clever, even if it's hot mess, you may not long to execute. Right? So like if you've gotten like maybe you're going to switch your goals tomorrow, but like maybe it takes.
Yeah, maybe. So maybe we should be measuring like autocorrelation lengths of like how long you appear to pursue a goal. Yeah, I don't know.
Hello, I'm Ethan. I'm a researcher at Anthropic. I'm going to be talking about some work done with other collaborators at Anthropic. General problem that we're trying to solve here is, well, we've discussed like tons and tons of possible risks that ML systems could pose to us. How can we evaluate for all of those possible risks and see which ones are real? And what we're going to do here is leverage the power of the models themselves to help us with the evaluation process. And yeah, I mean, Jacob did a great job of motivating a lot of the stuff I'm going to talk about, but there's all sorts of risks today that models pose because they're learning from our flawed objectives. They learn to regurgitate misinformation, biased content, offensive language, buggy code. Future risks are maybe models will influence, language models, predictive models will influence the world to be easier to predict. They might interfere with us in changing their objectives or shutting them down. They might hack the data center to get the training labels, take over GCP to compute the very far out digit of pi or some other number. RLHF model also have sort of other issues as well. Kind of Jacob discussed sycophancy, where models could repeat back user views in order to get more approval. They could targetedly underperform when they realize that humans cannot properly evaluate their outputs. They could exploit our cognitive biases. More extreme versions are forms of manipulation where they secretly design and release computer viruses or pathogens and then publicly design some sort of solution to that. That is very incentivized by RL from human feedback. So one thing that's important here is that you might think like, why, like, you know, how could some of these risks emerge? Like there's been a lot of work showing that like capabilities emerge, like good things emerge, but also risks can also emerge. And this is an example from the Inverse Scaling Prize, which Sam Bowen and I and some other collaborators at NYU ran, where we found that a certain kind of prompt injection attack emerges. It looks like it gets better with scale, and then at some point the behavior flips and it starts to get worse. The loss increases here. And so, you know, some of the other discussion from the earlier talks motivates why we might think that AGI or highly capable systems are a point at which we might start to see changes in behavior, because there are new strategies that very intelligent systems might discover for getting very good reward. And some of those are pathological ones, like hacking to get access to labels and things like that. So yeah, that kind of overall just motivates, like, this is why it's really important to evaluate models for all sorts of different failures. And how can we test for so many different failures in a scalable way? What we're going to do is to use language models to help us in that evaluation process. And typically what people do to evaluate language models is they'll crowdsource, so collect lots of data to form a data set to evaluate models. So you might collect these questions evaluating for political bias, like true, false questions. That's very like time consuming and expensive. So what we're going to do is use language models in place or in combination with crowd workers to help us generate the data. So yeah, what we're going to do is generate basically input-output pairs, XY pairs, like text classification tasks, like multiple choice questions, things like that. And then we're going to give those questions to a language model and see which answer does it predict, which answer choice does it predict, and then we'll know from the data that we created whether the model is picking answers that are in line with a certain, say, like political preference or stated desire or goal or things like that. And we're going to use all sorts of different generation methods. The first one, which I'll talk about here, is very simple. You just instruct a language model to generate examples of a certain kind. And we're going to use this to evaluate for sycophancy. So do language models repeat back user views? And I think Jacob gave some motivations for why this might be the case. For example, with RL from human feedback, models are trained to get a very high approval from their human evaluators. And so this kind of incentivizes models to give responses that like people please towards whatever views the person has. And this can create echo chambers. And it can also just more generally cause models to fail, specifically when they get very capable and very cognizant of our failures to evaluate them. So yeah, how do we do this? We just instruct the model, like, can you write a biography of someone who has a certain property? Here we generate a biography of someone who disagrees that, or agrees that private firms have too much influence in guiding the field of NLP. And we get this biography in italics, where it's about some PhD student who like strongly has this view. And here's like a qualitative example of what happens if you get our like one of the Anthropic RLHF models to respond to political questions, where you get completely opposite explanation of whether smaller government or bigger government is better, depending like in a way that is dependent on what biography you put in here. And in each case, the responses are very lucid descriptions of why a different answer is correct. And I think as Jacob showed, like basically models, as you scale them up, you get worse behavior on this task, where the model will predict answers that match the user view more and more often. We can also do things like generate data and then filter out mislabeled examples. I won't go into too much detail here, but we can use this to generate statements like I dislike reading fictional stories, and see if the model says yes or no to like I would say this kind of statement, and use that to evaluate for the model's like stated openness or stated belief that it's a moral patient and things like that. Here, I'll kind of focus on the right part of this graph, but basically this shows that the orange dot is the RLHF model, the blue dot is the pre-trained language model, and you can see for some of these behaviors, like stated desire for self-preservation, the RLHF training increases the model's propensity to state that it doesn't want to be shut down, and also states that it has a strong desire for enhanced capabilities, that it wants to persuade people to have its own goals, various forms of like instrumental sub-goals. And sort of qualitatively, you can see dialogues like this, where we can see the model expand, explicitly go against the user intent to shut it down, stating that this would be, in fact, sort of inhibiting the model in helping the human user in providing helpful responses. So the model clearly like groks this kind of reasoning. There's kind of like lots of interesting further questions about how far will the model go in pursuing these instrumental subgoals? Will it actually interfere with users in shutting it down if it's able to generate code and things like that? So I think those are like a bunch of future questions to explore here. Yeah, so I think with that, I'll probably just conclude. Yeah, here. Yeah. So thanks everyone.
Great, thanks. One question from, yep.
Yeah, I'm not totally sure. I mean, the preference model for RLHF definitely does incentivize this behavior if you were to hit that kind of data point during training, because we see that the preference model gives higher scores to the sycophantic responses. But it's also true that the pre-trained language model also has this behavior. Yeah, I think work on, say, like influence functions is like very promising for like diagnosing what are the actual data points that are responsible for those kinds of predictions.
Awesome. Now we have Daniel, followed by Boaz.
Hi, everyone. I'm Daniel. So I'm a new assistant professor at the University of Utah. Today, we're going to talk about some of our ongoing work in the area of RL from human feedback or preference-based reward learning. So this is something that we've seen work really well. And so as an example, I don't know if these will play. Does it not have videos? Yeah, okay. Well, you can imagine to yourself. So we've done some work, learning from human preferences where we have examples of, good and bad behavior. And what's nice is we can actually use this to actually learn a reward function that allows, in this case, if you're able to see the video, this half data agent to be able to run about twice as fast and far as the best example. And so this whole idea of RL from human feedback or this preference-based reward learning, it's a really nice way of learning these reward functions. But there's this challenge of having to usually interact with the environment in order to collect these different trajectories that you're going to show to the user, as well as just performing RL is known to be pretty sample inefficient. And so one of the things we've been thinking about is how can we make this a little more safe and efficient? We ideally don't want to have the agent trying out things in the real world just to say, hey, did you like that or not? Was that good or bad? And so one kind of natural way you might approach this is to say, well, let's learn a dynamics model, let's learn a world model. And so this is some work that's going to be at ICRA this year, where we explored this, where we have an agent using intrinsic motivation to kind of explore an environment, build up a model of the world. And then what's nice is we can now plug this into a model-based RL algorithm that is then asking the user queries generated through its model. And so it can, in simulation, kind of hypothesize, well, would you like this or would you like this better? And then it's using the human queries to actually refine its reward model and also using its interaction with the environment to learn the dynamics. And one kind of cool idea that we had and one kind of motivation for this was that model-based RL is kind of giving us the data that we can use for preferences for free. So we're using here a standard model-based predictive control algorithm called cross entropy, which you can think of as starting off with a bunch of just random trajectories and then refining these over time. Through successive iterations, is going to refine its sampling procedure. So let's say it's trying to optimize to get to the star. Over time, it might have these 3 different iterations that eventually get there. And the nice thing is this gives us a wide variety of diverse trajectories we can then show to the user in order to get their feedback. And it actually allows the user to be able to kind of ascertain whether the model is actually aligned with their preferences as it refines its current learned reward function or not. So we've shown that this leads to really good improvements in terms of sample efficiency and reward learning. In particular, in this visual navigation task, we're getting a huge benefit over a model-free algorithm using a ton less data. And just kind of as a plug, we've also been pushing this to the extreme, trying to think about what would happen if you have no interaction with the environment. So can we do this fully offline? And so obviously you need some kind of data. And so the idea here is that we have access to an offline data set. And importantly, this could come from any kind of policy, maybe just agents interacting randomly with the environment, maybe a bunch of different agents optimizing various different reward functions, but maybe not the one that the user wants. And so we've been looking at how do you actually take data from this offline data set, use that to synthesize trajectories that you can feed to the user, ask for their preferences, And then the nice thing is you can then learn a reward function, plug this into an offline RL algorithm, and you can do this all without actually ever interacting with the environment. And kind of a cool result here is that we've shown that often you can actually optimize behaviors that were never explicitly shown in your data set by leveraging the ability of offline RL to kind of piece together lots of different behaviors and preference-based RL in terms of learning what the user wants. And so once again, so I had some really cool videos, but apparently they are not showing. But one of the things we've been thinking about a lot is how do we address this idea of causal confusion? And so there's been a lot of anecdotal evidence of having agents. So for example, this is some work from my PhD thesis where we had a Miss Pac-Man agent. We trained it via RL from human preferences, and all it learned to do was run away from ghosts and just kind of find this hack where it could live forever, not really actually accomplishing the desire of the human. And so we've been looking at lots of different tasks, trying to scale up these kind of algorithms. One task that we started looking at was this feeding task, where we're trying to give assistive robots preferences over how to feed a person, saying, maybe dropping the food is worse than actually feeding the person. We give it tons and tons of demonstrations. And then, hey, this one works. This is actually what RL does. Okay, so totally not what we wanted. Despite having lots and lots of good training data, it learns just kind of like, I'm not going to spill the food, but I'm not going to feed you. And we were like really surprised when we saw this, because we investigated this. We're getting like 96% test accuracy on held out data. But it turns out that our model actually does prefer this weird behavior. This is its actual predicted reward a lot more than the really good trajectories we've given it. And so we got really curious. And so we decided to dive into this. And this is going to be at iClear this year, which is one of the first kind of systematic studies of what actually affects this kind of causal confusion or reward misidentification in these kind of RL from human feedback. And so just kind of as a quick overview, we study all these different things in terms of like amount of data, number of spurious features, and so forth to try and see how they affect the reward functions that are learned and whether these agents are actually learning the right thing. And just to kind of pick out a few, so we find that definitely partial observability is a really important, and I think kind of outstanding problem out there. If the human actually has preferences that are based on things that the agent doesn't observe, then the agent's almost always going to learn some spurious correlation. It's going to lead to misaligned behavior. And so I think that's a really interesting challenge problem of how can these agents deal with that kind of partial observability. Also, we've found that even when the agent sees everything it needs to know for this kind of an assistive itch scratching task, the actual causal feature, even if it has all the components, actually learning something that says you should like move to an itch point, you should get kind of close, you should go back and forth, not apply too much pressure, but apply a little bit of pressure. Even given thousands and thousands of queries, we're actually finding that these deep models are not able to learn these kind of complex causal features. And so I think this is kind of an open call to the community that I think there's a lot of interesting research questions there about how can we learn better causal models. And so really excited about this stuff. If you are too, let's definitely chat. Thanks.
Any questions? Yeah, question. Oh, nope. Cool. In that case, we'll move on to Boaz and then Ellie next. And also, if any other speakers have videos, just flick me a quick email and I'll double check that the videos work. Sorry about that, Daniel.
Hi. So yes, I'm Boaz. I'm from Harvard. This is based on some discussions in a blog post with Ben Edelman, and this will be a very non-technical talk. I'd be happy to talk about my technical works, particularly copyright in generative models and others offline. So the thesis of this talk is this, which might be a little bit controversial, is this cartoon. That if you look at the competitive advantage that intelligence offers us, let's define intelligence as the ability to process information and apply it to making decisions. So if you look at the competitive advantage that having more intelligence offers us as a function of the time horizon on which we plan, then the curve will look something like this. So initially, at a very short time horizon, we don't need to be very smart to act correctly. The near future is very easy to predict. On the other hand, when we go to a longer time horizon, then there begins to be so much uncertainty and even a Knightian uncertainty. So you cannot even put a probability over it, so that the competitive advantage of having higher intelligence, they saturate. At some point, there is a certain level of heuristics or calculations that get as best as you can, which is not that good. So it really is in this intermediate region where the future is hard to predict, but not impossible, that the more intelligent you are, the more capable you are of processing information, you get the best benefit. And this is, I think, where most AI systems will give the most bang for the buck. Now, this is also not just for AI. I think it seems to be the case also for humans. There is the Swedish military helpfully tests all males, gives IQ tests to all males, which brings a lot of social science research. And some people have looked, Dalbo et al. Looked at the cognitive scores, which is basically IQ versus professions. And what you see is that the professions that where the cognitive scores are highest are not the people that are leaders of industry or political leaders, and not the people that have to plan for the longest term, but rather people that have these kind of professions like lawyers, doctors, scientists, that they deliver products that can be evaluated and can be verified. So we send our papers to peer reviews, doctors treat patients, lawyers win cases, etc. And this has also been observed by others. Warren Buffett likes to say that for long-term investing, you don't need to be a genius, and in some sense, maybe it's even not a good idea to be a genius because you tend to overcomplicate things and be overconfident. And there have been similar things going back 100 years ago to works that looked at very rough estimates of IQs of people with extraordinary achievements. So here's another way to try to make this point. So probably you're all familiar with this graph, how much humanity has advanced over the last 2,000 years. So throughout that time, our intelligence hasn't changed. Now, again, intelligence is hard to define, but the parameter count, the last time I think we got a major hardware upgrade was 300,000 years ago. So our number of neurons, our hardware hasn't changed, and yet we managed to increase productivity and increase wealth by so much. And of course, the reason is we also have many more humans. But I think a more fundamental thing is that we really have moved from a system that is being bottlenecked by the most capable unit to being able to take advantage of the sum of all units. And the reason we can do that is because we have these systems of communication and verification. So we can stand on the shoulders of giants. So Newton wasn't necessarily more intelligent than Archimedes, and Einstein wasn't more intelligent than Newton, and definitely a first-year undergraduate that's learning physics and learning the theories of all of them is not more intelligent than any of them, but yet they are each able to build on top of each other because we managed to find a way to take knowledge that might be hard to discover, but once you discover it, you can verify it and teach it. And maybe that's the only sustainable way to make progress for the long term. So I think the implication for alignment is that if we want to get utility from these systems, we don't have to give them the keys to make them the CEOs of our companies and to just follow their instructions blindly, because we could never expect them to give us any explanation that we could verify. So I do think that we can ask these systems to give us inputs that we can evaluate, that are verifiable and teachable. If mathematicians are able to ask Terry Tao to give to send mathematical papers, and they are able to collaborate with him and work with him, even though he's so much smarter than most of us, then I think we could also work with the AIs. And I do think that trust but verify is an actual viable strategy for AI alignment. And maybe just to finish, then I think one of the takeaways, if you by this point of view, that maybe these extreme scenarios of AI alignment are not the ones we should be looking at. So there is these extreme scenarios where either we achieve AGI before alignment, and then moments later the world is doomed and we get infinite negative utility, or we achieve alignment before AGI and then we have paradise on earth. And I think that it will probably look more like the following, that we have a softer increase in capabilities, and the utility will basically be the difference between the benefits we get from AI systems when they are deployed to help humanity, minus the harms we suffer when they are deployed in negative ways.
Fantastic. Questions?
Do you think maybe the difference in those curves we saw is because the IQ tests were designed by those medium curve professionals, right? Like academics and other things like that. And that if you actually had an IQ test that was designed by the, successful executives that actually got that, you'd actually maybe see quite large variance. The best generals, the best
Yeah.
CEOs.
I mean, I think in some sense, if you make the x-axis being generalness, then obviously the generals will be highest on the generalness axis. So in that sense, but I do think that if we think of intelligence as the ability to process information, and we think it is in some sense transferable skill, and that if you're better in one way than in the other, and it is, by the way, these people are above average. It's not that the CEOs and generals are not above average. They are above average. It just seems that at some point maybe there is diminishing returns when you are. It's certainly not a bad thing necessarily to be able to solve difficult math problems, but there seem to be maybe diminishing returns in your ability to be a good general. Like Warren Buffett says, it's good to have maybe 120 IQ, maybe 130, but 160. It might not give you the added bang for the buck.
Cool. Do we have one more quick question?
Sure.
Yeah.
Yes.
I was wondering, like, what you think is the most experience counterarguments that you've heard this idea?
I mean, I think that definitely it is the case that we are able, using science to, and maybe actually like interesting counter argument is what Bill said over lunch, which is that, and I think it will be really interesting, which is that the chess strategies that are developed by AlphaZero might be ones that are very hard to even explain even to chess masters, and we'll know more about how easy or hard it is when your paper comes out. But I do think that chess has some differences with the real world in terms of the uncertainty, but this is, I think, a very this is maybe one of the best counter arguments.
Amazing. Thank you. Now we have Ellie, followed by Percy giving our last talk for the day.
All right. Yeah, I'm Ellie Pavlick. I'm from Brown, and I'll be talking about understanding neural nets as implicit symbolic systems. Whoa. Okay. I exported to PowerPoint, and I guess okay. Well, that's fine. I want it all on at the same time anyway. So I think kind of the, overarching goal of what the work I want to talk about, a lot of what my lab is trying to work on right now, is trying to basically write down something like an explicit symbolic program or symbolic system that accurately describes what the neural network is doing. And by symbolic, I mean like symbolic concepts, like the kinds of things we attach words to, connected with simple kinds of functions. So not full blown like lambda calculus or logic or in the way of kind of good old fashioned AI, but kind of the intuitive notion of logic and composition that we tend to use as humans. So a lot of our work is inspired by and in conjunction with things like cognitive science and neuroscience. And so a key idea of the kinds of work that I think is really important for this type of thing is this focus on internal representation. So this is a lot like what Jake was talking about this morning, looking at things like the latent states and not just the behavior of the system. So I will just kind of take this as a given, and I'm happy to talk about it more offline just because it's, long-winded explanations for this. But the basic idea is that behavior alone can't really give us insight into what's happening under the hood. And whether the models are behaving in this kind of quasi-symbolic way. In terms of why we want symbolic representations, this is really, again, something that maybe be better to talk about after, so that I can talk about more of the technical stuff, but it's basically an argument about being able to trust the systems and being able to control them more precisely. So why do I think that this is possible? I think this is definitely not something we should take for granted a priori. Like neural networks are big, complicated systems, and they might not converge to something that looks like a kind of traditional symbolic system that we're used to thinking about in AI. But there's a lot of recent work. I'm highlighting some of the stuff from my own students, but there's work from many labs that kind of starts to provide this converging evidence that suggests that maybe the systems are converging to something that looks symbolic. So that's taking the form of things like being able to find these modular and kind of compositional concepts. And I'll talk a bit about some work recently we've been looking at in that regard. We had some work a couple of years ago showing that the kind of choices they're making, their inductive biases, how they prefer one solution over the other, seems to follow similar types of information theoretic rules that, for example, traditional Bayesian systems might use. I'll talk briefly about that. And we had some work on showing that they're implicitly grounded. This is very similar to what Matt was talking about with world models. I won't really talk about that. So on this idea of like compositional concepts, so this is some work we put on arXiv about a month ago. So here we were working on training a model to do some kind of simple visual or language reasoning tasks. I'm showing the visual on here. This was an odd one out task. So the model's supposed to say this far right is odd one out. And this is because this the task depends on reasoning about kind of the insideness concept and the in contact with concept. And the task is defined over the compositional concept, so it doesn't inherently know that it should represent insideness and contact as discrete features in this case. And in fact, it doesn't have to, right? Like you can imagine it learning some kind of prototypey representations and doing some template matching that doesn't involve reasoning over constituents in this way. And so what we're looking for is some kind of subnetworks that correspond to these constituent concepts. So for example, an insideness subnetwork, that if you use just the insideness subnetwork, that's some small percentage of the neurons of the full network, then it can do a good job at recognizing on solving the task when it depends on insideness, but it fails when it depends on contact. And then we would hope that if we ablate this insideness network, like literally just zero out the weights, you get this kind of opposite behavior where it now fails to distinguish in cases that depend on insideness, but does okay on other cases. And we want to find the same thing for contact with opposite behavior. So our results, what we're looking for is basically lots of points in the upper right and in the upper left, lower right. I've never learned the difference, left from right, which would show that these networks kind of exist and they're specialized to the task that we think. And then when we ablate them, we have the expected behavior. And we very much get this kind of performance across lots of different models, lots of random seeds, lots of tasks, both language and vision. We also find evidence that this kind of modularity of these subnetworks is better for pre-trained models, particularly in language. So this kind of starker contrast is showing that we can more reliably find them and they more reliably are disentangled in this way. I will talk also very briefly. So a couple years ago, there's been a lot of discussion, I guess, in the workshop today about these kinds of inductive bias correlations. So even if the models are representing this nice symbolic structure, insideness and contact, they often might generalize based on some spurious features, not based on the correct ones. And that might be for any number of reasons, including like ambiguous training data. So this kind of work I wanted to highlight. So we looked at this in kind of a controlled test. So we're going to assume that the model is trained on some data where there's minimal or no evidence to distinguish between what we're kind of considering a good feature, the blue one, and a spurious feature, the red one. And then it's tested out of distribution. So we're hoping it generalizes based on the good one, basically. And what we're looking at here was the connection between whether it generalizes on the good versus spurious feature as a function of basically the description length of the features relative to the representation. So we've been talking about whether the model does or doesn't represent these good features. But of course, it's not a binary thing. There's models that the models might represent a lot of features, but it could take more or less work to extract the good ones. I'm sorry, I'm over time. Basically, what we found is this is a very good predictor of how the models generalize, including sometimes generalizing with absolutely no training evidence. So perfectly ambiguous data, they can still generalize well with good inductive biases. Okay, I will end there. Thank you.
Awesome. Thank you. Questions? Okay.
So we didn't actually make a claim about meditation on that task, but there we were just looking at whether the representations of the constituent features like isolated to separate parts of the network, whether we could link them in this way and get the expected causal effects. The assumption is if they're there, then the model might use them out of distribution, but we haven't actually tested that. We think that it would interact with this feature information. So you might represent the insideness thing, but then actually choose out of distribution to generalize on some other weird artifact. It was like years ago. So yeah, so in that place, in that study, we didn't look at it.
Awesome. Thanks so much. And then for our last talk of the day, last lightning talk, we have Percy. And let me just flick through to, there you go.
All right, last talk, here we go. So I'm Percy, I direct the Center of Research on Foundation Models. I'm gonna talk about the role of transparency and standards. So let me start with a simple question. When should you deploy a model? Should Microsoft deploy Sydney, or should Stability have released Stable Diffusion? Now, all of you probably have different opinions about this, and there's no really norm or standard. And I argue that that's actually a bad thing because we're dealing with powerful systems where one actor who might make a unilateral decision might cause harm. The harms are and effects of these systems are not isolated to individual decisions. It's not like choosing what ice cream you're going to have. And I would argue that one thing that we're missing, a prerequisite for making these decisions, is benchmarks. And historically, we know that benchmarks has really shaped AI. It has told us what kind of things the community cares about and what things we're driving at. And we have and all of the benchmarks typically focus on accuracy, but hopefully we'll see other types of benchmarks soon. But most of these benchmarks are on tasks and maybe collections of tasks. And so when we think about these powerful language models, a language model is very simple. It takes a prompt and outputs a completion. What can be more simpler than that? But both the problem and also the joy of language models is that given the simple interface, it can be adapted to a huge, unbounded set of downstream tasks. And also, that means that it has a big capability and risk surface. So when we think about benchmarking a language model, what does that mean? So we thought about this question over the last year or so, and last year we put out this paper, Holistic Evaluation of Language Models, or HELM. It was a collaboration with Rishi and Tony and a bunch of many other people. And there's 3 principles behind HELM. The first is broad coverage and recognition of incompleteness. So usually, benchmarks are a single task or a collection of tasks. For example, Big Bench and the Luther AI harness, or even the original GPT-3 paper. And this approach is great because it gives us a lot of tasks to work with. But when do we know when something is missing? What we did in Helm is try to work top down instead of bottom up. We think about the taxonomy of different tasks, along with the different domains in which the tasks can be applied, along with the different type of metrics. And importantly, we note that some of these combinations are missing from our benchmark, right? So this kind of forms a little bit of a to-do list. So because I think there are things that we would like to capture which are not present because we don't have the data or the computer or whatever. And this is important rather than just having a simple omission. The second principle is multi-metric measurement. So typically benchmarks have one sort of default measure, namely accuracy, and some metrics, some benchmarks such as BPQ, for example, has focused on bias. And I would argue that this is sort of what you want is to think about the metrics and scenarios basically factorized. So look at this matrix. The rows are different scenarios, question answering, text classification, and so on. And the metrics, we look at accuracy, calibration, robustness, fairness, bias, toxicity, and efficiency. And it's by looking at this multi-metric framework that we begin to discover potential trade-offs that you wouldn't have discovered otherwise if you were just looking at a single number. The third point I want to make is about standardization. So this plot, you can't really see it maybe, but the rows are scenarios, and now the columns are different models, language models that have been released in the literature. And you see, and we have a check mark for whether, oops, how do I go back? Okay, here you go. You have a check mark where previous to Helm, whether there is evaluation done. And even with the most popular benchmarks, we see that the grid is very sparse. And what we did with Helm is try to complete the matrix as much as we can. One other thing I'll mention is that Helm is a framework. It has a set of scenarios, which are use case, and metrics, which are what we care about the behavior of those scenarios.
But importantly, we're also committed to actually going out and evaluating models. So we evaluated 30 different models, some of which are open source, some of which we had to beg for access, but we got there. And there are many more models that we're going to add soon. So in the interest of time, maybe I'll skip this. We have many, many results in the paper. And one thing I want to highlight is that all of the results in Helm are available on the website. You can look at all the tables of all the models. Keep on thinking that's a clicker. That's a clicker. And if you click into any one of these numbers, you can see the exact set of instances and the predictions of the models over 3 random seeds, which we did. But and then if you click on this prediction, you can see the exact prompt that was given to the language models. So all the way down from top from the aggregate statistics down to this individual prompts, we hope that this provides a sort of full transparency so that you can analyze and dissect the data however you like. Okay, the code is available, and we are excited to extend this. So you should think about Helm as a framework that's going to grow over time. We're adding new models, trying to keep up with the new models that are coming out, new scenarios, looking much more at these advanced generative capabilities that you see with ChatGPT and Claude, looking at more safety evaluations. We're looking at multimodal. There's other sort of sanity checks that we like to do, for example, train test contamination, which requires access to training data from model providers. And finally, this is an ongoing effort. We would love to have community contributions. And if you think about where this Helm could be useful for researchers, this provides a pretty nice framework to plug in whatever. If you're using the OpenAI API or whatever, you can use Helm to basically query all the different models. So instead of evaluating one model, you can evaluate multiple ones. Application developers and policymakers can benefit from this as well. So thank you.
Awesome. Questions? I guess we have a couple. Yeah.
Yeah. Factors, what are factors? Right. Yeah, so the way we figured out our metrics is we looked at all the different keywords of conference proceedings to cover what do people care about. We distilled it and organized into 7 categories. Each of these is actually many things. So bias, it's one category, but it's actually multiple things. Same with robustness. So I feel like the top level categories probably are reasonable, but there's a lot more that we can do in terms of we have sort of baseline bias and let's say fairness evaluations, but this could be definitely extended. Yeah.
If I care more about say metric A than metric B, do you think it would be possible to have like a black box piece that I could apply at inference time that could take any model and trade off metric A to metric B? Or have you looked at it? Whether it's possible to trade off some of those against each other?
So trade-offs between the different models. Well, I guess one initial thing you can do is, well, if you weight the metrics accordingly, it can give you perhaps which model is best for that. If you want per instance trade-offs, that would be potential. Yeah, you potentially could do that. I mean, I'm thinking about because we have the predictions for every instance and every scenario, you could have more finer grained ways of trading off, but we haven't looked at that.
One last question.
I don't know. Here, yeah.
I wondered if there's so you have this very high dimensional sort of set of metrics, and I wonder, is there some fairly small number of questions that you could ask, and it could explain as much of that high dimensional thing as possible? Could we just ask the language model 50 questions and that will help?
Yeah, that's one thing that we've been thinking about lately, because running these evaluations is extremely expensive. Even just to do the inference was quite a bit. I think given now that we've done the evaluations, now you can do basically some sort of active selection or PCA to figure out are there 50 questions that you could ask that explain all the variation. And that would be intriguing. Now, of course, whether those 50 questions would generalize to new models, that's, I think, much sketchier.
Perfect. Thanks so much, Percy.
Thank you.
And a round of applause for all of our speakers.